Reaction mechanisms. Well, that harpoon mechanism that I just mentioned is an example of a reaction mechanism. Most chemical reactions occur in several steps. It's not just a one-step thing. When we look at a chemical equation, we're usually just showing the substances that are present at the beginning and the substances that are formed by the reaction. Those are the things that we can look at. There's actually often many steps in between them, and those are harder to figure out. But the reaction mechanism is the series of individual reactions that occur in that overall reaction. The steps in the reaction mechanism are called elementary steps, and each of those represents the exact species that are colliding in the reaction. So let's look at the reaction for hydrogen and iodine monochloride. And these are the two steps that occur. Hydrogen reacts with the iodine monochloride and forms hydrogen iodide and hydrogen chloride. And then the hydrogen iodide reacts with the iodine monochloride and forms hydrogen chloride and iodine. The overall reaction is what we get when we add these two together. So here we have hydrogen iodide being formed, and here we have hydrogen iodide being consumed. So those essentially cancel out. So the overall reaction is we've got H2 reacting with two ICLs to form two HCl's and one iodine. This is the overall reaction between hydrogen iodide and iodine monochloride. It shows what you start with and what you end up with. But the mechanism shows the individual steps. Hydrogen iodide is produced in one step and consumed in another. It's called a reaction intermediate. It wasn't present at the beginning, it's not present at the end, but it is present in the middle. The steps in the mechanism have to add up to the overall chemical reaction. The reaction mechanism actually gives us a lot of information about the reaction and helps us to understand how we could control it and make it do what we want. And so it's very, very useful. It shows the actual individual collisions that are occurring. But how do we figure out what the mechanism is? Because in that example, the HI was formed and then consumed. How can we measure that it was even there? How can we figure out what those individual steps are? Well, chemical kinetics, what we've been talking about up till now, is what helps us to figure out what the mechanism is. So you measure the kinetics of the overall reaction, you know what the overall chemical equation is, and then you work backwards to figure out a mechanism that's consistent with those observed kinetics. These elementary steps can be characterized by the number of reactant particles. That's called the molecularity. So a unimolecular step is where you have one molecule reacting to form products. So that would be a decomposition of some kind, right? Bimolecular is where you have two different particles reacting to form products. Those two particles could be the same, or they could be different from each other. Okay? So these are both bimolecular because they involve two particles. There are termolecular steps. Those would have how many? Three. These are very rare, though, because you have to have a simultaneous collision of three particles with enough energy and the correct orientation. Does that seem like a real high probability event? No, not so much. They do happen, but they're rare. So we will mostly see unimolecular and bimolecular elementary steps in these mechanisms. The rate law for the overall chemical reaction cannot be figured out just by looking at the equation. But in the elementary steps of a mechanism, you can determine just by looking at the equation for that elementary step. It depends on the molecularity. So if we have a unimolecular step where we have A going to products, the rate law will be that the rate is equal to the rate constant times the concentration of A. If we have two A particles reacting, that's a bimolecular. The rate will depend on the square of the concentration of A. Here we've got two different particles. It's also bimolecular. But here it's going to be the rate constant times the concentration of A times the concentration of B. And then you've got the termolecular ones. These are more rare. But here we see that it's the number of A's reacting is the exponent. Here we've got two A's and one B, so this is A squared times B. Here we've got three different things reacting, and so we've got A times B times C. So these are there, they exist, but these are the ones we're going to look at the most. So the molecularity equals the overall order. Here we've got first order with respect to A, first with respect to B, first with respect to C, but that adds up to 3. Here we've got second order in A, that's the same as the molecularity. So we've got these multiple elementary steps. They generally do not all occur at the same rate. Usually one of them is going to be slower than the others, oftentimes much slower. And that's called the rate determining step. Because the reaction has to go through all of the steps to get to the products. And if there's one step that's really slow, that's going to slow the whole reaction down. It's a little bit like traffic on a freeway. Here they're repaving one of the lanes, and so they've got 2 lanes blocked off, and you've got 3 lanes of traffic coming in here, and you've got this bottleneck, right? This is going to slow down the rate of traffic. They can go much faster before, they can go much faster after they get through here, but this is going to slow down the rate. And that's what the rate limiting step does. It controls the overall rate of the reaction. So let's look at an example. NO2 reacting with carbon monoxide to form and carbon dioxide. So experimentally, we can determine the rate law to be the rate is equal to the rate constant times NO2 squared, the concentration of NO2 squared. How do we determine the rate law? One method was the initial rates method, and you look at the initial rate and at different concentrations, and so you might take 1 molar and 1 molar and see what the rate is, and then double this and keep this one the same and see what does that do to the rate of the reaction. We talked about that last week. Okay, so experimentally we determine this. Could this be a single-step reaction? If it's a single-step reaction, then this is the elementary step and represents the actual collisions that are occurring. The rate law of an elementary step can be predicted by looking at the equation. So if this was the elementary step, what would the rate law be?
NO2 and then CO.
The rate would be the rate constant times the NO2 concentration times the carbon monoxide concentration. But that's not what we observe. So this is not a one-step reaction mechanism. So the answer to that is no. That might be confusing. No. So here's a possible mechanism. That NO2 reacts with NO2 and forms NO3 and NO. And that NO3 reacts with CO and forms NO2 and CO2. That this is the slow step and this is a fast step. What do these add up to? Yeah, it adds up to the top one, right? Thank goodness. Yeah, and these guys cancel out. I reversed the order here, but that doesn't matter. So this is the slow step, and this is the fast step. Once we get through this one, the rest of it's going to go just fine.
How do you figure it's going fast?
Well, we'll see. In this example, that first step has the higher activation energy, and thus the smaller rate constant is going to be slower. It's going to determine the overall rate, and that will predict that the rate law for the overall experiment is the same, the overall reaction is the same as the rate law for that first step. Once we get up here, it goes down. It has, I think of it as, this is not like a golf course or anything, but I think of it as hills and gravity. If you get up to this point and you roll something down the hill, it's going to have enough momentum to get up and over that one and keep going down, right? So this is the holdup right there. We need to go back. So if this step here is going to determine the overall rate law, what's the rate law for this step? Remember, elementary steps, you can predict the rate law from the equation for the elementary step. It's going to be K times, there's two of these, right? NO2 squared. And that's the same as this. We figured this out experimentally, and then we came up with a mechanism that gave us the same result. That suggests that this is a good mechanism. So there are two conditions for a valid mechanism. The elementary steps have to add up to the overall reaction, and the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. So we can't prove mechanisms, we can only validate them. These are the conditions for a valid mechanism. You could come up with more than one mechanism that fits both of these conditions. The reactions add up to the correct equation, and they predict the same rate law. And so to figure out, like if you have two of them, to figure out which is correct, then you need more data. You need more information. So that reaction that we looked at, the first step was slow and was the rate limiting step. What if the first step is fast? If the first step is fast, then the rate limiting step is probably going to contain those intermediates, those reaction intermediates. And that's kind of a problem because then the rate law with those intermediates is not going to correspond to the experimental rate law. So what do? Well, if the first step is fast enough, we might get an equilibrium established. So we've got the reactants in the first step and the products are being formed so fast that there's time for them to go back. We've got an equilibrium. We've got reactants forming products, products forming reactants. Because these products are waiting around on that second step. There's that bottleneck in the highway. They can't get through yet, and so they're just like, what do we do? Well, let's go back. Let's go back to that rest stop and get another can of soda. And then we'll come through here and try again. I don't know. So an example. Hydrogen and NO reacting to form water and nitrogen. This is our observed rate law. And this is the mechanism. Here we have 2 of the nitrogen monoxide reacting to form dinitrogen dioxide, N2O2. This is fast. Here's our rate limiting step, the second step, where hydrogen reacts with the N2O2 to form water and N2O. And then we've got another fast step at the end. And if you add these together, you do indeed get this overall equation. But the observed rate law has hydrogen and nitrogen monoxide. And this slow step doesn't, right? Let's go to the next slide. So if we look at this slow step right here, what's the rate law that we would predict? Oh, wrong way, wrong way. I'm in the right place now. The rate should equal K times what? H2 and N2O2. That's what this step predicts. But N2O2 is an intermediate. It's not one of the reactants. And so how does that agree with the observed reaction rate? The observed, if I can remember correctly, was that the rate equals the constant times H2 and NO squared. Is that right? Let's go back. H2 NO2 squared.
Well, because that N2O2 is the same thing as 2NO.
Yeah, we have an equilibrium going on here. And so this has a rate constant. We'll call that K1 in the forward direction. What do we know about the rate of the forward and the reverse reaction at equilibrium? They're the same. So the reverse is K minus 1, and those are going to be equal. And then we'll call this one K2. And there's a K3, but that one was also fast, and so we're not going to worry about him. So for that first fast equation, the rate, I'll call that rate 1 being forward. The forward rate would equal K1 times what? NO squared, right? This is an elementary step. We can predict the rate law by looking at the equation. This is bimolecular, 2 NOs colliding, and so it's NO squared. What's the rate law for the reverse reaction? We'll call that rate minus 1. It's going to be the reverse rate constant times what? Times N2O2. How many people did I just lose?
What do you do with the coefficient on the K1?
Yeah.
This is the rate constant for the forward reaction.
Yes.
The reverse reaction has its own rate constant.
Yeah, well, so you just change the coefficient from the 2 NO.
So the rate for the forward reaction is the forward rate constant times NO squared, because that's the reactant. The reverse reaction is going backwards.
Yeah.
So here's the reactant. There's only one of them, so it's N2O2. And the reverse reaction rate constant is K minus 1. So the reverse rate I'm calling rate minus 1, and the forward rate I'm calling rate 1. At equilibrium, these are equal, right? The forward rate is equal to the reverse rate. So K1 times NO squared must equal K minus 1 times N2 O2. You okay with that?
Yep.
So what we're trying to do here is we're trying to express the N2O2 concentration in this predicted rate law in terms of the reactant in the overall mechanism. So we want to get this NO in there instead of the N2O2. So we could take this guy and solve for N2O2. So that says that N2O2 is equal to K1 times NO squared divided by K minus 1. You okay with that? Now we can take this guy here and press the wrong button on the iPad. There we go. And substitute it in here. So now we have that the rate equals this constant times, what I'm going to do is I'm going to pull these constants out and stick them in the front. Oh, this really should be K2. I knew something was missing, right?
Yeah.
Because that's predicted from this, so it's K2. So I've got K2 times K1 over K minus 1. And then I've got H2. And then I've got the rest of this. And I've got the NO squared. Now that's looking really close to this, isn't it? This is a constant. What if we just take all three of these constants and lump them together as one constant? Then we get this constant times H2 times NO squared. Ta-da! Any questions? I hope you guys like algebra. Yes?
How do you get rid of all the constants over there?
Okay, what I did is I just made a new constant called K. Oops. It's just some number, and we don't know what those numbers are anyway. And so what we're saying is that K is equal to K2 times K1 over K minus 1. We're just lumping them together. Any other questions? We're almost done here. Just did that one. So there's an example, 13.9, which does a similar thing. I encourage you to look at that in your textbook and work through it. And then this is the for practice one, which is a little simpler. So we're going to do this one. Predict the overall reaction and rate law that results from this two-step mechanism. How do we predict the overall reaction? We just add these two equations together. Right? So there's an A2 on one side and an A2 on the other side. So we're going to end up with 2A plus B is going to form A2B. How do we predict the rate law? It's the rate law for the slow step. In this situation, the slow step is the first one, and so we don't have to do what we did in the last slide there. The rate will equal a rate constant times what? A squared. If the first step is fast, then you have to do that looking at an equilibrium and rearranging and substituting in to get rid of the intermediate concentrations which cannot be measured. Beautiful blank slide.